We will now use the concepts of energy that we developed earlier to solve problems. Let's start with this problem. A constant force of 75 Newton acts on an object initially at rest and acts through a parallel distance of 0.6 meter. What is the final kinetic energy of the object? B. If the object has a mass of 0.2 kilogram, what is its final speed? What is the work that would be required to bring it to rest? Well, what all this problem involves is the basic definition of kinetic energy. Alright, what do we have? We have a force is 75 Newton. The displacement produced by that force is 0.6 meter on a mass m equal to 0.2 kilogram. So what is the work done? The work done is force multiplied by displacement in the direction of the force, that is 75 Newton times 0.6 meter, that is 45 joules. What are we supposed to do? What is the final kinetic energy of the object? What is the definition of kinetic energy? Kinetic energy is a measure of the work done to give an object a velocity v. So this is the measure of the work done on the object. So the work done on the object is a measure of its kinetic energy. K, kinetic energy, is a measure of the work done on the object. Therefore, the kinetic energy of the object is 45 joules. Now, if the kinetic energy of the object is 45 joules, what is the final velocity? Kinetic energy is a measure of the work done to give an object a velocity v. And when the object has a velocity v, its kinetic energy will be 1/2 mv squared. Is that right? So kinetic energy equal to 1/2 mv squared. We know the amount of kinetic energy, that is 45 joules. We know the mass of the object, that is 0.2 kilogram. And therefore we say 1/2 mv squared equal to 45 joules, and solve for v squared from there. Look at the way I'm going to solve for v squared. It will be 2 multiplied by 45 divided by m. I hope you can follow that calculation like this. 2 multiplied by 45 divided by m will be v squared. And that gives me v squared equal to 450 meter per second squared. And so what is v? V is the square root of that, which is 21.2 meter per second. Okay, what's the answer for C part? What is the work that needs to be done to bring this object to rest? If you remember the definition of kinetic energy that we used, kinetic energy is a measure of the work done to give an object a velocity v. That is one definition. It is also equal to the work that needs to be done to bring the object to rest. So, if our object has a kinetic energy of 45 joules, what is the amount of work that you need to do to bring this object to rest? It is opposite to that. It should be negative 45 joules. 45 joules of work is done to give the object a velocity of 21.2 meter per second. To reduce this velocity to 0, the work that needs to be done will be opposite, will be negative 45 joules. Okay, let's do another problem. A 600-gram object with an initial velocity of 3 meters per second in the positive x direction is acted upon by a force in the direction of motion. The force does 2.5 joules of work. What is the final velocity of the object? Well, the force does 2.5 joules of work. What does that 2.5 joules equal to? When the force does 2.5 joules of work, that is a measure of the increase in kinetic energy, the gain in kinetic energy. The object is moving with a certain speed, and on that moving object, a force does work. How much work? 2.5 joules of work. That means that amount of work done increases its kinetic energy. So 2.5 joules is a measure of the increase in kinetic energy. Let's take our data. The mass of the object is 600 gram, that is 0.6 kilogram. The initial velocity is 3 meters per second, and the net work done is 2.5 joules. If K1 is the initial kinetic energy and K2 is the final kinetic energy, the change in energy delta K must be equal to the net work done by the external force. Is that right? Yes. So delta E, the change in energy, is K2 minus K1. Now K1 is 1/2 mv0 squared, the initial kinetic energy. Because the object is moving with this velocity 3 meters per second, it has an initial kinetic energy 1/2 mv0 squared. Let's use those values. M is 0.6 kilogram, V0 is 3 meters per second, and therefore the initial kinetic energy is 2.7 joules. Therefore, according to work energy theorem, delta E equal to the change in the energy is a measure of the net work done on the object. So K2 minus K1 equal to the net work done. How much is the net work done? Is 2.5 joules. So K2 minus K1. K1 is 2.7 joules. Therefore, K2 minus K1 is 2.5 joules. And that gives you your final kinetic energy. Therefore, K2 equal to 5.2 joules. What are we supposed to find? We need to find the final velocity. We know the final kinetic energy. If the final velocity is V2 or V, then this final kinetic energy will be 1/2 mv squared. Alright, let's do that here. If V is the final velocity, then K2 will be 1/2 mv squared. And that K2 equal to 5.2 joules. And now, you know the mass of the object. The only unknown quantity there is V. Solve for V. Look at that again. I solved for V squared. V squared is 2 times 5.2 divided by M. And M we know is 0.6 kilogram. So that will be 2 times 5.2 is 10.4. M is 0.6 kilogram, and therefore V squared is 17.3 meter per second squared. V is the square root of that is 4.2 meter per second. I hope you understood the method which we used to solve the problem. It is the work energy theorem. The change in the energy is a measure of the work done by the external force. Another problem. A girl swings back and forth on a swing 4 meters long. The maximum height she reaches is 2 meters above the ground. At the lowest point of the swing, she is 0.5 meters above the ground. What is the girl's maximum speed and where does she attain it? Now picture this problem, a swing going back and forth. Now this is the ground and here is the girl on the swing. And we will consider first one extreme position where she's at the left extreme, at the maximum height. That is where she is now. At the maximum height, the velocity will be 0. Is that right? The swing comes to a maximum height where it stops and then it goes back. You notice that what happens here is the swing is taken to a height. It has potential energy. When you leave it, the potential energy changes to kinetic energy, and that kinetic energy changes to potential energy, and the oscillations of the swing is simply the change in energy from kinetic to potential, well, potential to kinetic to potential to kinetic, and so on. So at the maximum height at the left extreme, the velocity is 0 and the height is 2 meters. It says at the maximum height she reaches 2 meters above the ground. Now what is the energy that she has here? Because she is at a height h from the ground, at a height 2 meters from the ground, she has potential energy. What is the potential energy? U1 equal to mgh1. What is the mass? Well, we don't know the mass, so we're going to leave it as m. G is 9.8, h1 is 2 meters, so 9.8 times 2 is 19.6 times m. The potential energy at this height is 19.6 m joules. What is the kinetic energy at this position? Kinetic energy equal to 0. So we say at this position K1 equal to 0, U1 equal to 19.6 m joules, where m is the mass of the girl. The total energy at the maximum height is K1 plus U1, that will be 19.6 m joules. Okay, what happens? This potential energy is now going to change to kinetic energy. She's going to fall back to the equilibrium position. The speed is maximum at the lowest point. You see, that is where all this potential energy, you can see, at this position when she is at the extreme, there is only potential energy here. When she reaches the lowest point, all that potential energy gets converted to kinetic energy. Now this is the case of the swing. If you notice, you pull it to one side, it has now potential energy, and because it has potential energy, when you leave it, it falls, and you can see the energy conversion. When it falls back to the lowest position, it has maximum speed, and because of the maximum speed, it climbs to the other extreme. You see, it cannot stop at the lowest extreme because in falling it has acquired a speed. So where does it have maximum speed? Maximum speed happens at the lowest point. There is no speed at the highest point. All the potential energy is converted to kinetic energy at the lowest point. Alright, let's use this to solve this problem now. The speed is maximum at the lowest point from the ground. So the swing is come now. This is the lowest point. The speed is maximum there. V equal to V max. And at the lowest point, H2 equal to 0.5 meter. So she is 0.5 meter above the ground at the lowest point. So this height is 0.5 meter. That means she has a certain amount of potential energy and a certain amount of kinetic energy at this point. If K2 is the kinetic energy there, that K2 will be 1/2 mv max squared. The velocity there, or the speed there, is the maximum speed, and I'm going to call it V max. So the kinetic energy K2 at the lowest point is 1/2 mv max squared. The potential energy at that point is mgh2, and that will be, what is mgh2? Now we don't know m, so we leave it like this. G is 9.8, h2 is 0.5 meter, so 9.8 times 0.5 is 4.9. So mgh2 is m times 9.8 times 0.5, that is 4.9 m joules. That is the total, that is the potential energy at that point. What is the total energy at the lowest point? There will be potential energy U2 plus the kinetic energy K2. That is 1/2 mv max squared plus 4.9 m. Alright, we now know the total potential energy at the highest point. And well, we now know the total energy at the highest point. What is the total energy at the highest point we calculated? I think it was 19.6 m. That was the total energy at the highest point. And the total energy at the lowest point is 1/2 mv max squared plus 4.9 m. Well, the total energy must be the same, is that right? Energy can change from one form to another. At any position of the swing, the total energy must be the same. Conservation of energy demands that K1 plus U1 equal to K2 plus U2. The total energy cannot change. It must be conserved. That means K1 plus U1 is 19.6 m joules. K2 plus U2 is this quantity, 1/2 mv max squared plus 4.9 m. Now look at the beauty of this equation. You see m appears in every term. You can divide by m throughout and that will disappear. That means the only unknown term is V max. We can now solve for it. So dividing by m and multiplying by 2. Well, multiplying by 2 will eliminate this 2 here. So what will you get? Dividing by m and multiplying by 2, this will become, what is that? 19.6 times 2 is 39.2. Multiplying this term by 2 and dividing by m, m will go, 2 will also go. That will be only V max squared left there. And dividing by m and multiplying by 2, this will become 9.8. 39.2 equal to V max squared plus 9.8. Solve for V max squared. V max squared is 39.2 minus 9.8, that is 29.4 meter per second squared. Therefore, V max is square root of that, 5.4 meter per second. You see, the neat way to solve problems using the conservation of energy. Okay, another problem. A 2.4 kilogram box is placed on an inclined plane of inclination 37 degrees. If the coefficient of kinetic friction between the box and the plane is 0.3, what is the minimum force required to move the box up the plane with a uniform velocity? And what is the minimum force required to keep the box from moving down if mu s equal to 0.5? Well, I know you will say this has nothing to do with conservation of energy. Well, that is true. This is something that we did earlier. So this is a problem purely on friction. I want to do it anyway. Okay, we have an inclined plane of inclination 37 degrees, and you have a box of mass 2.4 kilogram on the inclined plane. Now let's look at the forces on this box. This is just a review from the 2 lessons, is that right? 2 lessons away. What are the forces acting on the box? The weight of the box equal to mg. M is 2.4 kilogram, g is 9.8 meter per second squared. So the weight is 23.5 Newton acting vertically down. Alright, can you tell me the other forces? What is the component that is pulling the box down the plane? The component of this force pulling the box down the plane is mg sine theta, mg sine 37. mg is 23.5 Newton, so that will be 23.5 sine 37, and that is 14.1 Newton. That is the force pulling the box down the plane. Well, what is the force acting up the plane? If the box is going to slide down, then the friction is going to act up the plane. The force of kinetic friction is, do you remember? What is the equation for force of kinetic friction? Where the box is sliding down, is that right? If the box is sliding down, then the friction is the force of kinetic friction. Fk is mu k Fn, mu k times the normal force. What is the normal force pressing the 2 surfaces together? That will be mg cos theta. So the force of kinetic friction will be Fk equal to mu k mg cos 37 degrees, which is mu k is 0.3, mg is 23.5, we know that, times cos 37, and that is 5.6 Newton. Now the question is, in what direction is that frictional force acting? Well, friction always opposes motion. So the direction of the frictional force is opposite to the direction of motion. What does the A part say? What is the minimum force required to move the box up the plane with a uniform velocity? I want to move this box up the plane. So in what direction will the friction be acting? If you want to move the box up the plane, the friction is now going to act down the plane. And now, you don't want to create an acceleration on the box, do you? No. We don't want a net force. We want to balance the force. That's all we want. Because what we want is, we want to move the box up the plane with a uniform velocity. When the box moves with uniform velocity, there is no net force on the box. That means the total downward force need to be overcome by an upward force so that the net force is 0. Alright, when you move the box up the plane, what are the downward forces? Well, mg sine theta always acts down the plane. That will be always downward. And now, because you are moving the box up the plane, this frictional force Fk equal to 5.6 Newton is also acting down the plane. It is opposing the upward motion. So the total force now acting down the plane is 14.1 plus 5.6. And in order to balance that, you need to apply the same amount of force upward. Alright? Since we want to move the box up, the frictional force Fk acts down the plane opposing the upward motion. So the frictional force Fk equal to 5.6 Newton is also down the plane for this part of the problem. And therefore, what is the minimum force that you now need to apply upward? The minimum force must therefore balance these two downward forces. So that F minimum therefore must be equal to 14.1 Newton plus 5.6 Newton, that is 19.7 Newton. A force of 19.7 Newton applied upward will make the box move uniformly without an acceleration. There is no net force on the box at that time. Alright, how about B part? What is the minimum force required to keep the box from moving down? This time, the box is not going to move. We need to keep it from moving down. That means the force of friction will be static friction. Alright, tell me, we are now trying to prevent the box from moving down. That means the tendency of the box is to move down. If the box has a tendency to move down, the friction will oppose that. So this time, the friction will be opposing that tendency to move down. And the frictional force this time is the force of static friction, which is mu s mg cos theta, mu s mg cos 37 degrees. Mu s is given to be 0.5, mg is 23.5 Newton times cos 37, and that is 9.4 Newton. So when you place this block on the inclined plane, this frictional force is preventing it from sliding down. But because the downward force is 14.1 Newton, this frictional force alone will not keep it there. You need an additional upward force to prevent it from sliding down. The question here is, what is that additional force? When the box tends to slide down, I know many of you have problem understanding this concept. I have seen it in my class before. When the box tends to slide down, the force of static friction is acting up the plane. Is that right? When you place the box on the inclined plane, the box wants to slide down under this force, 14.1 Newton. And the friction is going to prevent it. So the friction is going to act up the plane. Now, so we have a frictional force, the static friction, that is 9.4 Newton acting up the plane. The force of static friction, Fs, now assists the applied force, F minimum, to prevent the block from sliding. That means if you now want to keep the box from sliding down, we need to balance the downward force with the upward force. So the F minimum added to the frictional force must balance the 14.1 Newton down the plane. So you're going to apply an F minimum, that is the green arrow here, upward, and the sum of the red arrow and the green arrow upward must balance 14.1 downward. So we say F minimum plus 9.4 Newton equal to 14.1 Newton, and that gives you the F minimum as 14.1 minus 9.4, that is 4.7 Newton. Okay, let's now go back and do a problem that directly involves work, energy, and the work energy theorem. A 20-kilogram girl slides down a playground slide that is 3.2 meter high. When she reaches the bottom of the slide, her speed is 1.3 meter per second. How much energy was dissipated by friction? If the slide is inclined 20 degrees, what is the coefficient of friction between the slide and the girl? It's a very nice, good question. So concentrate and see how this is done. So we have a girl on a slide sitting on top. Obviously she has potential energy. Alright, so when the girl is on top of the slide, her height is 3.2 meter, there you are, and her velocity is 0, her mass is 20 kilogram. Her kinetic energy is 0. She's happily sitting there, enjoying her doll. She has no kinetic energy, but she has a potential energy. U1 equal to mgh1. And what is that? M is 20 kilogram, G is 9.8, H1 is 3.2 meter. Using those values, we have her potential energy when she is at the top is 627 Newton. Potential energy, is that right? It's not Newton, it must be joules. So correct that Newton to joules. Her potential energy at that height is 627 joules. What is the total energy at the top? The kinetic energy is 0, the potential energy is 627 joules, therefore the total energy is 627 joules. Okay. When the girl is at the bottom, what is the situation we have? Well, she's sliding down. Okay, let's make her slide down one more time. You can see when she slides down, a lot of energy is spent in doing work against friction. Is that right? Watch her sliding down. There you are. And in sliding, she acquires a speed. How much is the speed? At the bottom, her speed is 1.3 meter per second. And when she settles down, her height is 0. That means her kinetic energy is 1/2 mv squared. 1/2 I write as 0.5. M is 20 kilogram. And V squared is 1.3 squared. So she has a kinetic energy of 17 joules at the bottom of the slide. What is her potential energy? Because the height is reduced to 0, the potential energy is 0. The total energy at the bottom is kinetic energy plus potential energy equal to 17 joules. Well, you notice that she had initially 627 joules of energy, and when she lands at the bottom, her energy is just 17 joules. What happened to the rest of the energy? The rest of the energy is dissipated in doing work against friction. the net change in the energy is a measure of the work done against non-conservative force. That is an important factor here. So delta E, the change in energy, is E2 minus E1. This is negative 610 joules. And this negative 610 joules has been lost in doing work against friction. That is what slowed her down. Remember, if this friction was not there, she would be landing with a neck-breaking speed. Okay. Now, in part A, using work energy theorem. What is the work energy theorem? The net change in the energy is a measure of the work done by external non-conservative force. Delta E equal to is a measure of the net work done. Therefore, the net work done, which is a measure of the energy dissipated by friction, is negative 610 joules. You must be able to interpret the net work done. The work is done against the friction, and that energy is dissipated. In other words, we say it is lost. But can energy get lost? No, it can only get converted to other forms. What are the different forms into which this dissipated energy gets lost? Well, it gets lost in the form of, you can see, ask the girl, her bottom got very hot. You see? And the swing and the slide itself got hot. And there was some sound produced, there were some vibrations, you see. This energy dissipated actually got converted to many other forms. That is what happened. Conservation of energy is a true principle. W net equal to negative 610 joules is a measure of the work done to overcome friction. So the energy dissipated by friction is 610 joules. Okay, what is the next part? That's very important. If the slide is inclined at 20 degrees to the horizontal, what is the coefficient of friction between the slide and the girl? Now tell me, if you remember, what are the quantities you need to measure the coefficient of friction? The quantities you need to measure coefficient of friction are, if you remember, coefficient of friction mu equal to the frictional force divided by the normal force. That means we want to know the frictional force between the girl's bottom and the slide. We need to obtain that. And the normal force. In other words, what is the force pressing the girl onto the slide? That is the normal force. Those are the two values you need to obtain the coefficient of friction. Let's do that. The slide is inclined at 20 degrees. So this angle is 20 degrees. Now let's put the child somewhere on the slide here. The weight of the child is mg, that is 20 times 9.8, 196 Newton is acting vertically down. Alright, now remember, the child is now sitting on an inclined plane of inclination 20 degrees. What is the normal force Fn? Remember, the normal force Fn is mg cos theta. mg is 196 Newton. Therefore, that is 196 cos 20 degrees. That is 184.2 Newton. That is the normal force pressing the girl onto the slide. And that is an important quantity here. So, that means Fn equal to 184.2 Newton. We obtained the value of Fn. We now need the frictional force. Now, we have one thing under our belt. We know the total work done by the frictional force. Is that right? How much is the work done by the frictional force? We calculated that is 610 joules. And the displacement of the child got displaced. The distance the child moved is the length of the slide. If L is the length of the slide, the displacement of the child is L, which is the length of the slide. Now, the frictional force is acting on the slide, and the displacement L is in the same direction. Well, opposite, of course. So, if I draw this triangle, the hypotenuse is the length of the slide, then I can write, in the right triangle, L has the hypotenuse and 3.2 meter is the height of the triangle, the height of the slide. This is the height 3.2 meter, which is the same as this. And the angle is 20 degrees. Can you therefore obtain the value for L? In this right triangle, L is the length of the slide, 3.2 meter is the height, is the opposite side of this angle 20 degrees. Therefore, sine of 20 degrees is opposite side divided by the hypotenuse. There you are. 3.2 divided by L. 3.2 divided by L. Opposite side divided by the hypotenuse is sine 20. Therefore, L equal to 3.2 divided by sine 20. I hope that can be understood. Is that right? 3.2 equal to L times sine 20. Therefore, L equal to 3.2 divided by sine 20, and that is 9.4 meter. You see, that is a great big slide. I don't think that little child would enjoy that. It's a great big ride. Well, if F is the frictional force, we are looking for that frictional force F. Is that right? This force. Now, this force produces this displacement. Therefore, work done by the frictional force is the frictional force multiplied by that displacement. And that quantity must be equal to 610 joules. So, WFK, what does that stand for? Work done by the force of kinetic friction is the force of kinetic friction multiplied by the displacement. The displacement is the length of the slide, which is 9.4. So Fk multiplied by 9.4 is the work done by the frictional force. And we know its value is 610 joules. And therefore, we can calculate Fk. What is Fk equal to? Fk is 610 joules divided by 9.4, and that is 64.9 Newton. And mu k is Fk over Fn. I'm sure you now remember, we started with this a little while ago. Mu k is Fk divided by the force of kinetic friction divided by the normal force. Now, the force of kinetic friction is 64.9 Newton. The normal force is 184.2 Newton. So that will be 64.9 divided by 184.2. That is 0.35. The coefficient of kinetic friction between the slide and the child is 0.35. That has been a good problem. I like that problem. So review it and make sure that you understand the basic concepts. of using the conservation of energy and work energy theorem to solve problems like this. All right? Well, we have now solved core problems using the conservation of energy and work energy theorem. And I'm going to stop here. I will see you for lesson 3 later on. But one more time, let me remind you that your learning ability, your ability to understand the new concepts depend on how much you have learned the materials we covered so far. And that means doing your homework. All right? Okay, I will see you for the next lesson later on.